Let's take a look at how we might view one particular situation of wetness of grass being caused by rain in the language of probability. As before, when we studied Bayes' rule, we break it up into cases. So for our situations, we have rain occurring out of a total of n observations or n days. Out of those, in m cases, we have the grass being wet, and in a certain situation we have both rain occurring as well as the grass being wet for I cases. So we have data, which is simply W being yes or no, rain being yes or no, and lots of such data, and we can simply compute the probabilities that rain and wetness either occur or don't occur in the following way. So the probability that it rains and the grass is wet is I over n. The probability that it doesn't rain but the grass is still wet is m minus I over n. That it rains and the grass is not wet is k minus I over n. And the probability that it neither rains nor the grass is wet is n minus m minus k plus I over n. Notice that we had to add in I because these m cases included I, so did these k cases, so we had these overlap cases coming twice, so we had to add them back in since they were subtracted twice when we subtracted m and k. Well, a table like this is called a probability table or also a potential. Now, suppose one wanted to find out the probability that it rained or didn't rain. Well, one could simply do that from the data directly by simply adding up all the cases where it rained and dividing by the total. Similarly, adding up all the cases where it didn't rain and dividing by the total. Or one could work with this smaller table where one had already done some of the calculations beforehand, but forget about W, that is, sum it out, in the sense that you sum all the rows up, and wherever we have the same values of R, we simply add up those rows regardless of what the value of W is. So the first row and the third row get added together, the second row and the last row get added together, resulting in the following, which is clearly the sum of the first and the third and the second and the fourth, which is also called the marginalization of the W column. In other words, we have gotten rid of the W variable by summing it out wherever the values of R are the same. You can easily verify that by marginalizing out W or summing it out, one does indeed get k over n, which is the probability of rain being true, and n minus k over n, which is the probability of rain being not true. Now notice that in the language of SQL, marginalization is equivalent to an aggregation on the column P. For example, in SQL, one would write it as, if you think about this as a table, select R and the sum of P from this table, group by R. That means wherever there is an equal R, you keep a separate row in the result, but add them all up. Only keep distinct rows where there are distinct values of R. In the language of relational algebra, this is written as follows. We have a aggregation operation, which is a sum grouping by R on the table R, W. It's quite interesting that one can perform this operation on the probability table using SQL, and we shall exploit this fact as we go along. So please take a careful look and understand this. Now let's see how we might write Bayes' rule in terms of these potentials or probability tables. Remember that Bayes' rule stated that the joint probability that R and W together is the conditional probability of R given W multiplied by the probability of W itself, which was in the simplest case of yes and yes, we were simply writing I equal to n, rather I by n, as I over m times m by n, simple arithmetic. Similarly, for every other row, we would simply rewrite the denominator m by the appropriate value so that we get the conditional probability over here, and the probability of W falls out in this term. Verify this and remind yourself of Bayes' rule from the Listen lecture. Now let's notice how this multiplication actually takes place. Consider these as three tables, T0, T1, and T2. T1 has Rn W, but T2 has only W. Now let's see how we might multiply these two probability tables in another way. The probability that R given W multiplied by the probability of W is some way of combining these two tables, and that some way just happens to be the join of these tables in SQL on the common attribute W. Suppose we were to perform this following SQL. Select R, sum of the product P1 and P2 from these two tables respectively, where W1 equals W2, and group by R. So essentially all we're saying is we're going to multiply out I over m by m over n. Similarly, for the other case where R equal to yes, we'd also multiply k minus I by n minus m by the corresponding value in this table where W has the same value n, and then add this term and this term up, and you can easily verify that will give me k over n, which is the probability of rain being yes. Similarly, for the case of rain being no, one can work it out that the result of the SQL will get the correct value n minus k over n. To conclude, we can multiply probability tables, or rather potentials as they are often called in the probability literature, using SQL. Now let's turn to another important element, which is evidence. Suppose we have a joint probability distribution, like probability of rain and wetness, and we find that the grass is actually wet. In other words, we have observed some evidence, and that evidence tells us that the grass is wet. So W equal to Y. We need to restrict this table to only those entries where W equal to yes. So essentially we're saying let's drop all the entries where W equal to no and restrict it to W equal to yes, and that's this restriction operator, which is called the application of evidence to this potential. If we once again expand this restricted table using Bayes' rule, which is just a subset of what we had earlier, we get the probability of R given W equal to yes, which is just a restriction of the overall probability that of R given W, times the probability that W equal to yes. We don't have to worry about W equal to no anymore. In other words, we say that probability of R comma W restricted is the probability of R given W equal to yes times the probability of the evidence, which is the probability that W equal to yes. Now, coming back to SQL, it turns out that applying evidence is the same thing as using the select operator on the table R comma W. which is just this table. So what we did is multiplied PRW by the restriction operator, which is the same as doing a select. In other words, select RWP from this table where W equal to Y. That's fairly obvious. The a posteriori probability of R given evidence, which was just this, is now merely the restriction of the joint probability to the case W equal to yes divided by the probability of the evidence itself. Notice that if we did that division, we get exactly this table, which is exactly what we wanted, which is the a posteriori probability of R given W equal to yes, which is different from the probability of R in general. We'll work out an example in a short while, but for the moment, just notice that the actions of multiplying probability tables is just taking a join in SQL. The act of taking evidence, that is, observing one of the variables or one or more of the variables, is merely issuing an appropriate select statement in SQL. So let's now take a look at what all this means for the case of classification or abductive reasoning, which is what we were interested in the first place, which will bring us back to the language of classifiers and the naive Bayes classifier, but this time in terms of probability tables rather than individual probabilities.